Unit 3. Misconception in High School Chemistry. Unit Introduction. Students' misconceptions before or after formal instruction have become a major concern in science education because they influence how students learn new scientific knowledge, play an essential role in subsequent learning, and become a hindrance in acquiring the correct body of knowledge. Learning science is a cumulative process, and each new piece of information is added to what students already know about the topic at hand. Students bring to lessons a lot of pre-existing alternative conceptions about scientific phenomena that can interfere with students' learning of correct scientific principles or concepts. This understanding caused increased concern about revealing students' difficulties prior to, during, or after the instruction, in conceptualizing scientific knowledge and suggesting ways of remediation. Every teacher should know misconceptions for the lesson he or she teaches, in order to use the appropriate teaching methods. Unit Learning Outcomes. On successful completion of this unit, you will be able to identify possible student misconceptions in high school chemistry, design effective strategies to teach and avoid students' misconceptions in chemistry, develop classroom materials that can be used in identifying and challenging misconceptions in chemistry, specify the possible sources of chemistry misconceptions and find out mechanisms to solve them. Use different conceptual change methods in teaching to overcome students' misconceptions. 3.1. Students' misconceptions in chemistry. In-text question. In science, there are often many ideas that are frequently misinterpreted. This may be the result of students coping with making sense of abstract concepts. Also, since science is constantly changing, some misconceptions may be due to old ideas, while adapting to new discoveries and methods. Learning science is a cumulative process, and each new piece of information is added to what students already know about the topic at hand. Research has shown that children bring to lessons a lot of pre-existing alternative conceptions about scientific phenomenon that can interfere with students' learning of concepts, scientific principles or concepts. Posner, 1982. Tabor, 2000. Alternative conceptions. Students' misconceptions before or after formal instruction are of major concern because they influence how students learn new scientific knowledge, play an essential role in subsequent learning, and become a hindrance as acquired the correct body knowledge. Alternative concepts may arise as a result of the variety of contacts students make with the physical and social world, or as a result of personal experience, interaction with teachers, other people, or through the media. Gilbert et al. 1982. Griffiths and Preston, 1992. These ideas may be present before any teaching of a topic, and are often also found after teaching has taken place. According to constructionist theory of learning, knowledge is uniquely constructed by each individual learner, and learners actively constructed knowledge to make sense of the world, interpreting new information in terms of existing cognitive structures. The particular knowledge that is constructed by an individual will be affected by the learner's prior knowledge and experience, and the social context in which learning takes place. Tabor and Wattles, 1997. Students' pre-existing beliefs influence how students learn new scientific knowledge and play an essential role in subsequent learning. Children's difficulties in science occur because students' concepts before teaching are not taken into account, and therefore communication between teachers and learners cannot overcome. These ideas are logical, sensible, and valuable from the student's point of view, strongly held by the students, but may be significantly different from accepted scientific viewpoints, and may not be in conformity with the true or the scientific explanation. Osborne, 1982. It was also found that beliefs are widely held by learners in various grade levels, and are fairly stable and resistant to change by conventional teaching strategies, and are often the completion of formed science instruction. Preconceptions in chemistry are extremely persistent. Study on the evolution of preconceptions describe rapid evolution in fundamental ideas about chemistry at lower grades, but only very slow change thereafter. In spite of intensive instruction in chemistry, R.T. and Varjoli, 1998. The persistence of elementary alternative conception at high school level was also documented. This shows that concepts built by students during their first exposure to chemistry is important because the misconceptions they build are so resistant to instruction. These preconceptions from the mental framework, the scaffolding, on which students build all subsequent knowledge. New information and ideas which students receive are reinterpreted and rearranged to fit within the scaffolding. In-text question: students' strong preference for common sense reasoning, everyday analogies, visible effects and changes, and common non-scientific word usage leads them into many misunderstandings. Some classes of preconceptions are culturally specific, a product of the analysis and metaphors common in particular cultures or built into particular languages, rather than being unusual. Teachers have the responsibility of leading students to the correct use of analysis and metaphors, by indicating their limitations, to avoid misconceptions arising from different analysis and metaphors. Many alternative conceptions may be generated by students as they grapple with information and models presented in school which they are unprepared to imagine or understand. The teaching of atomic theory before students have fully explored the nature of matter at a macroscopic level will make them not to rely on atomic theory in explanation of physical phenomena. The difficulty of students not believing in something they can't see, and chemistry in predominantly occurring on the most abstract level, the symbolic level, contributes to misconceptions observed in chemistry. Activity 3.1 3.1.1 Misconceptions about acids, bases, and neutralization. Acids and bases are among the most familiar of all compounds. Students learn about acids and bases at lower grades and at high school level. They have different ideas about the nature of bases and the reaction between acids and bases, i.e. neutralization reactions. The concepts of acids and bases are taught based on different definitions of acids and bases. The term acid was used first to express substances that changed the color of certain plant materials. Later, Arrhenius developed acid-base concept based on dissociation of acids and bases. Acid is a substance that produces hydrogen ions, protons in aqueous solution, and a base is a substance that produces hydroxide ions in aqueous solution. Bronsted further developed an acid-base concept related to the function of particles. Acids are proton donors that give up protons, and bases are protons acceptors that take up proton. The Lewis concept of an acid considers acids as electron pair acceptors and bases are as electron pair donors. Acid-base concepts are discussed in chemistry class using these three concepts. There are considerable misconceptions that occur when students learn about acids and bases at different class levels. Different misconceptions of students related to acids and bases are discovered by researchers which show common misconceptions that exist among students. In-text question: acid and base chemistry is one of the basic concepts in chemistry because many of the reactions are acid-base reactions. The concept is related to other concepts such as chemical equilibrium, chemical reaction, stoichiometry, and solutions. The idea of acid was first used by Boyle in the 17th century, which was based on change in color of a certain plant extract. Lavoisier, Davy, Liebig, Arrhenius and Bronsted further developed the acid-base concepts. When students learn about acids and bases, most of them develop misconceptions about acids and bases. Students' prior experiences, background environment, worldview affecting their interpretation of observations, concepts, etc. can make students to come to the classroom with some misconceptions towards the topics to be taught, such as acids and bases. There are different misconceptions related to acids and bases found in literature. According to research done by Sebastian Musley cited by Barker et al., 2009, many students understand acid as something which eats material away and have aggressive effect. They consider also testing for acid can be done by trying to eat something away, and strong acids eat materials away faster than weak acids. Here students didn't use particle idea but a continuous, non-particle model for acids and bases. The idea develops in students who learn to think of acids as dangerous. Some students understand acid as substance that contain H+ ions and others as acid release protons H+, which is based on Arrhenius concept. These understanding might have been based on learned and remembered facts which don't show that students understood the notion of acid particles. Acids are not perceived as being particulate, but rather continuous matter with special properties. It was found out also many students have misconception considering all substances containing H are acidic, and those containing O are basic. There are many substances that contain H and are not acidic, such as hydrocarbons and sugars. Similarly, there are substances that contain O which are not basic, such as alcohols. This is due to students not considering the particulate nature of acids and thinking only the Arrhenius point of view. Acids are substances. Acid-base strength is another source of misconception. According to Sumfuleth and Geisler cited in Barker et al. 2009, for most students acid strength is solely based on the pH value of solutions. They consider strong acid have a higher pH value than weak acids. Their misconception is that strength and concentration of acid mean the same thing for them. They consider weak acids to be less concentrated and strong acid more concentrated. This shows misconception of relating strength with pH value. A pH value pH scale is a scale which is used to indicate the concentration of proton H+ in a solution. It is defined as pH equals -log H+. Many students apply this definition in a different way, as simply pH value is negative logarithm to the base 10, pH 7 is neutral to skin, etc. When students were asked about what they understood about a solution which have a pH of 1, only 15% mentioned a 0.1 m solution of hydrochloric acid solutions like HCl and H2SO4 without mentioning the concentration, and 45% didn't even answer the question. Most students also understand a pH equals 0 no acid is present, rather than as 1 m solution of an acid. This shows lack of true understanding of pH values by students or inability to apply neutralization as one of the reactions of acids and bases. Students have different misconceptions about the concepts of acids and bases, which are partly discussed above. Acid-base misconceptions of students have effects also on concept of neutralization, giving rise to some misconceptions about neutralization reaction. Activity 3.2. Neutralization is a common reaction between acids and bases. It is used to be defined as the reaction between acid and base which consume each other. This is what the term neutralization indicates, from the Latin word neuter, meaning neither of the two. According to the modern definition, neutralization is a reaction between H3O+ and O particles producing water due to proton transfer reaction. A common misconception about neutralization is that the neutralization of acids and base always gives a neutral product. Most students, when asked to show chemical equation using types of particles involved when hydrochloric acid reacts with sodium hydroxide solution, they write the common equation. Students mostly do not use the representation H+ AC and OAC ions react to produce H2O. They have the opinion that all particles, positive and negative charges, react with each other forming NaCl molecules. When students are asked about an aqueous solution of 1NaO added to an aqueous solution of 1MCH3, they explain as it contains equal amounts of H3O+ and O ions. This is the result of the misconception that the molar concentrations of H3O+ and O are equal and neutralize each other in all neutralization reactions. Empirical studies on the concepts of neutralization showed that in the first step students conserve as it is obtained the salt solution, that is, sodium chloride solution, in the example of neutralization reactions commonly given. In the section step, the evaporation of water from the salt solution and formation of solid sodium chloride. When interpreted by students, many of them thought that sodium ions were linked together to form NaCl molecules, that the changes are thereby neutralized. The students mix concepts of acid-base neutrality and electrical neutrality, as NaCl solution is neutral because Na+ ions and Cl ions bond and charges are neutralized. the charges are neutralized in crystal. Equal numbers of Na plus ions and Cl ions neutralize each other. Crystalline material is the result of a neutralization. Therefore it is neutral. The charges balance each other out in the compound. The compound is neutral. It is therefore important to use the term neutrality entirely to the acid-base topic, and not to argue with electrical neutrality of ions in solution or in crystals, but to argue on the basis of equilibrium of anions and cations, or with that of charges, to avoid the misconception. Students think about the idea of neutralization along the lines of acid-base equilibrium. It was found out that they assume after neutralization, sodium chloride solution contains the same amount of hydrochloric acid and sodium hydroxide. With neutralization there exists equilibrium of acid and base. The dissolution of solid sodium chloride in water to form a salt solution is not correctly recognized as dissociation by most of the students, which assume that it is the inversion of neutralization in which the same amount of acid and base are found in the solution. This result shows that students do not have the correct understanding that when salts dissolve in water the ions only get hydrated. H2O molecules surround the ions of the salt. O and H3O plus ions are not involved, and if we mix an acidic solution with a basic solution, a salt will be produced which contains neither ions nor H3O plus ions. In-text question 3.1.2 Misconceptions about states of matter. There are different kinds of substances such as water, iron, butane, wood, meat, stone, sand, etc., and these exist in different kinds of physical states: solid, liquid and gas. Each kind of substance has a usual state: iron, solid, water, liquid, butane is a gas, etc. These substances can sometimes be changed. For example, many substances will melt if you make them hot enough, and others will burn. Any liquid will freeze if you make it cold enough, and will boil and change to vapor. Some solids decompose, i.e. change slowly into some other substances. These changes of substances are understood in different ways. Students have some misconceptions about the different states of matter. The concept of solids, liquids and gases by students of lower grades is based on the thinking of metals and wood as typical solids. To them, substances which are not hard and rigid cannot be solids. So classifying solids which do not fit this image is difficult. They usually do not classify non-rigid solids such as dough, sponge easily a solid, because they think the easier it is to change the shape or the state of the solid, the less likely it is to be included in the group of solids. Water is the standard liquid against which other possible liquids are compared, and is considered as a typical liquid. Generally, children classify new liquids more easily than solids, perhaps because liquids are less varied in their physical characteristics. When reasoning about matter, they rely solely on sensory information, and ideas about particles are not readily used to answer questions about the properties of matter, so children persist in thinking that substances are continuous. Gases cause special difficulties for students since those commonly experienced like air are invisible. Gases are not considered as matter because most are invisible. This invisibility prevents them from forming a concept of gas spontaneously, and instruction is needed for students to acquire knowledge about gas properties. Students have an idea: substance can disappear, but its taste and smell stay behind. Some students' naive view of matter are: a matter has no permanent aspect. When matter disappears from sight, e.g., when sugar dissolves in water, it ceases to exist. B. Matter has a materialistic core to which various random properties having independent existence are attached. Matter can disappear, whereas its properties such as sweetness can continue to exist completely independently of it. C. Weight is not an intrinsic property of matter. The existence of weightless matter can be accepted. D. Simple physical transformations such as dissociation are not grasped as revisable. These statements are supported by evidences obtained from students as to explain the decrease in water level in a large tank after sunny weather. Most focused on the remaining water, seeing no need to explain whether missing water had gone. For them, the matter had simply ceased to exist. Statement A. When students were shown propanone evaporating in a closed tube, they taught that the propanone disappeared and its smell remains. Statement B. When solute is dissolved, they think as it disappears. Students' reasoning is inconsistent about the status of matter. They use sensory reasoning on some occasions and logical reasoning on others. Sensory experience dominates in cases where substances are visible. Students' thinking about matter is influenced by their naive view, which leads them into incorrect answers in solving particles problem. The persistence of a naive view of matter is a major source of misconceptions related to states of matter. Activity 3.3. Students' naive view of matter is based on the seeing is believing principle. Particles cannot be seen, so they do not need to exist in a functioning model to explain the behavior of matter. The basic learning problem requiring learners to overcome immediate perceptions which lead to a continuous, static view of the structure of matter is accommodated in students' naive view of the physical world so as to include a new model adopted by scientists. Internalizing the model therefore requires overcoming basic cognitive difficulties of both a conceptual and a perceptual nature. Teaching using appropriate methods can bring about change in children's thinking. In their 1998 study, Novich and Nussbaum showed that after teaching students about the three states of matter, they found out that the use of particle ideas to answer a wide range of questioning about the state of matter has increased from 60% to 90%. Those students who don't use particle ideas use the bulk properties of substances instead. This was seen from the answer given by such students in response to the question concerning the change in temperature of a block of ice. As temperature rises to -1 oC, the ice will melt, causing the block of ice to get smaller. In explanations given by students, some of them think water molecules in steam are larger than those in ice. This type of explanation seems to be an intermediate stage between full appreciation of the particular nature of matter and naive ideas about car tire pressure during a journey. When a car goes on a journey, the tire starts to warm up and this causes pressure. These are low-level macroscopic answers given by students who think of matter as continuous. Many students who appreciate that matter is particulate do not give up all their naive view, so ascribe bulk properties to particles themselves, as particles can change their form, e.g. solid to liquid, explode, burn, expand, change shape, add color, or shrink. The notion that particles are in constant random motion and that empty space exists between particles causes students considerable difficulties. Students don't usually attribute dye diffusion to explain why gas particles, which are uniformly distributed in a vessel, don't fall to the bottom, relating to the fact that the gas particles are in constant motion. The notion that empty space exists between particles causes another difficulty, where students think that, although the particles were themselves discrete entities, the space between them is filled, for examples, with dust and other particles, other gases such as oxygen and nitrogen, air, dust, maybe a liquid or unknown vapors, etc., or was non-existent. For example, the particles are closely packed, there is no space between them, or no place is completely empty. Most students find space difficult to imagine and use a space-filling model, and intuitively fill it with something. Since students depend on visible, sensory information about solids and liquids to develop their naive view of matter, their difficulty accepting a model proposing there is nothing in the spaces between particles is obvious. Activity 3.4 3.1.3 Misconceptions about chemical bonding. Chemical bonding is one of the most important topics in chemistry, and the topic involves the use of different models, from simple analogical models to abstract models. It is also a topic that students commonly find problematic and develop a wide range of misconceptions. It needs the understanding of the concepts of electron, ionization energy, electronegativity, molecular structure and stability to explain why and how chemical bonds occur. Chemical bonding has been classified into three systems: covalent, ionic and metallic bonding. There have been numerous studies to determine students' understanding and misconceptions about metallic, ionic and covalent bonding. These students reveal the presence of different misconceptions among students. General misconceptions related to chemical bonding identified by a study made by Robinson 1998 and Taylor 2001 are outlined below. Chemical bonds form in order to produce filled shells, rather than filled shells being the consequence of the formation of many covalent bonds. Ionic bonds are the transfer of electrons, rather than the attractions of the ions, that result from the transfer of electrons. The reason electrons are transferred is to achieve a full shell. Atoms need filled shells. Molecules form from isolated atoms. An ionic bond only occurs between the atoms involved in the electron transfer. Thus, sodium ion forms one ionic bond to a chloride ion in solid sodium chloride. Na+ and other ions are stable because they have a filled outer shell. Equal sharing of the electron pair occur in all covalent bonds. Polar covalent compounds contain charged species. Non-polar molecules form when the atoms in the molecule have similar electronegativities. The largest atom exerts the greatest control over the shared electron pairs. Ionic compounds from neutral molecule and water. Misconceptions dealing with ionic bonding overemphasize the process of electron transfer and explicitly use the notion of ion pairs as molecules and imagining ionic compounds to exist as discrete molecules. Ionic bonds are considered as unidirectional, focusing only on atoms involved in the electron transfer. The attractions of ions formed as a result of electron transfer are not considered as ionic bond. In covalent bonding, students relate covalent bond to sharing of electrons, not considering the influence of electronegativity that results in unequal electron sharing. They relate the polarity of a bond to the number of valence electrons in each atom involved in the bond, which they think are possessed specifically by the atoms. The strength of a covalent bond is related to intermolecular force between molecules, and not to intermolecular force within the molecule, i.e. between atoms. Misconceptions in chemical bonding are generated in the process of knowledge construction, well as emphasis on the transition between the symbolic macroscopic and microscopic representation. Each process in chemical bond formation and compounds forms must be represented correctly at each level of concept presentation in the process of teaching chemical bonding. Activity 3.5. Activity 3.6. 3.2. Common sources of misconceptions in chemistry. Misconceptions are observed in students, teachers, and even scientists. Historical concepts and échanges have shown how scientists developed their own concepts with some misconceptions in the past. Misconceptions result from the interaction between learners and environments. Characteristics of misconceptions are personal, incoherent, and stable, and are embedded in students' alternative belief system. There are different possible sources of students' misconceptions. Some of these possible sources of students' misconceptions are: 1. Prior knowledge and experiences of the learners which are not compatible with scientific concepts. 2. The use of everyday languages and metaphors which have different meaning from chemistry terminologies. 3. Students not properly taught different basic concepts at micro level. 4. Teachers not properly understanding and teaching concepts, and lack of knowledge of students' misunderstanding. 5. Students lacking visualization of models of concepts. 6. The nature and proper sequencing of the concepts learning. In-text question 3.2.1. Students' preconcepts. Students developed their own concepts which are based on their observation, and come up with their own ideas of the world. These ideas are developed without having any prior knowledge. They pick up ideas from their interaction with environment and society. These self-developed concepts may not often match up with scientific concepts. These ideas are not necessarily wrong, and are described as alternative, original, or preconcepts. They are pre-scientific ideas that students bring to school. Teachers should know these preconcepts of students to make connections between the newly attained knowledge during instruction and the well-established preconcepts. It is common to come across several preconcepts at the beginning states of scientific learning at the elementary, middle, and high school levels of chemistry. The following are some common examples of students' preconcepts. Sun and Earth. Students' idea about the Sun and Earth is one common example to show students' preconcepts. Most children's first experiences regarding the Sun are accompanied by comments made by their families and neighbors. The sun will rise in the morning, at midday it will be at its highest point, and in the evening it will set. Observations regarding sunrise, sunset and its own cycle must lead the child to the idea. The sun cycles around the earth. Students imagine also the earth to be a disk over which the sky stretches parallel. The sun, the moon and the stars are to be found in the sky. Greek natural philosophers developed similar ideas before 2,000 years ago, which was corrected at the end of 16th century by Copernicus. Combustion. When students talk about combustion, saying that something disappears and observe that the remaining ash is lighter than the original portion of fuel, then they have done their observation well, and have come up with logical conclusions. The concept of a carrier of properties copper turns black by heating with a flame, as well as concepts of destruction wood is burned, goes back to students' preconcepts of burning that students have in mind. After several years of observing burning processes, i.e. of paper, wood, charcoal, sprints or gas, students are led to the statement that something disappeared and only a few ashes remain. When students are taught about process of combustion as the reaction of substances with air or oxygen and the mass of the substance increase after burning, they explain this observation based on their preconcepts. When students were asked what actually happens to the particles of magnesium metal when burned in air, they argued that the part of the magnesium disappeared into the air, and another part remains in the form of white ashes. Similar ideas are shared by students regarding the burning of iron wool decreases after burning. This destruction concept is also persistent in students who have learned chemistry for many years. The use of particles as a generic term for atoms, ions and molecules is related to the common use of particles by students. In everyday language, the term particles is used to show a small portion of matter. Chips of iron filings could also be called ion particles. Crystals of powder sugar crystals also as sulfur particles. Small sulfur crystals known as sulfur particles. When atoms are introduced to students, the diversity of the term increases, and the hydrogen atoms and oxygen atoms have become the smallest particles of water. This logic makes students to think that hydrogen and oxygen escape when water is boiled. Students' preconception of particles as a small portions of materials create a problem for students in understanding of the scientific particle term assorted to the submicroscopic level. For students, it is necessary they distinguish from the context when the term particles are meant in the sense of the particle model, or particles as a generic terms for atoms, ions and molecules. Activity 3.7 3.2.2 School-made misconceptions. Misconceptions are not only attributed to students, but are also caused by inappropriate teaching methods and materials used. Teachers' methods of instruction can lead students to have misconception if they're usually using traditional approaches. When students get involved in a subject matter that is more difficult despite competent and qualified teachers, they can develop school-made misconceptions. The following are few examples to show this. Composition of salts. This is a very well-known school-made misconception of students which arises from Arrhenius' theory of dissociation. He postulated that salt molecules are found in solid salts as the smallest particles, and decompose into ions by dissolving in water. Later, with the concepts of electrons, the misconception that atoms of salt molecules from ions through electron exchange was developed. Now it is recognized that there are no salt molecules, that ions exist all the time, even in the solid salt. By dissolving the solid salt, water molecules surrounded the ions, and hydrated ions are not connected. They move freely in the salt solution. One can observe even today, this historic misconception is quite common. Sodium chloride consists of sodium and chlorine atoms. Each chlorine atom takes an electron from the sodium atom, so the chlorine atom will have a negative electrical charge, the sodium atom a positive one. This type of misconceptions are also observed in the subject of chemical, where mostly electron pair bonding is elaborated on ionic bonding. The result is that students will not have any lasting concept of ions in an ion lattice. This is the misconception that has been developed during lessons, that is, it is school-made misconception. The same types of misconceptions can even occur if ions in the recommended issue of electrolysis of salts have not been correctly taught. Chemical reactions. It is a traditional in chemistry lessons to separate chemical reactions from physical process. The formation of metal sulfides from its elements by releasing energy is described in every case as a chemical reaction. In contrast, the dissolving of substances in water is often regarded as a physical process, because matter does not actually change. The dissolved substance can be regained in its original form through physical separation procedures. If one takes sodium hydroxide and dissolves it in a little water, a colorless solution appears and releases heat. The solution conducts electricity and produces a high pH value. Critical students regard this solution as being a new material, and the production of heat shows an exothermic reaction. From this example one can see it does not make any sense to separate the transformation of matter into chemical and physical processes. If we routinely continue to do this in the sense of we have always done it this way, automatic school-made misconceptions would arise based on teaching traditions in school. Composition of water. Water is composed of hydrogen and oxygen. One often hears these or similar statements in classrooms about compounds, which supposedly contain certain elements. These expressions arise from a time when it was common to analyze and find out which elements make up certain compounds. Insiders know the background of these statements. For novices, however, they will lead to school-made misconceptions. Students would associate the substances copper and sulfur in the black copper sulfide, particularly as experiments show that one can remove these elements out of copper sulfide. It would be better, in introductory class, to point out that one can obtain the elements from the compounds. Later on, if one is aware of atoms and ions as the smallest particles of matter, one can expand on these statements that the compound contains special atoms or ions, that one water molecule contains 2 H atoms, and one O atom connected and arranged in a particular spatial structure. But the pure sentence water contains hydrogen and oxygen will develop school-made misconceptions. Activity 3.8 3.2.3 Methods of overcoming misconceptions in teaching chemistry. Misconceptions in chemistry may arise due to different factors. The learner may be unable to construct a mental representation because of lack of relevant prior knowledge, excessive mental demand, not knowing what is relevant, or failing to notice elementary relationships within the new information and between it and prior knowledge. There could be a failure to manipulate a mental representation or relate it to others because of a lack of rules for governing the relationship. In-text question. Teaching process takes into consideration students' development stages which make it possible to change from preconcepts to scientific concepts. Individuals are given the chance to construct their own learning structures. Meaningful learning occurs when the learners actively construct their own knowledge by using existing knowledge to make sense of newly gained experiences. The first step in constructivist learning is to make the teacher and student aware of the learner's current idea. Teaching methods used in classrooms by teachers should support these ideas. Teaching can then be planned that challenges misconceptions and provides students with the opportunities for conceptual restructuring. Teachers play an important role in teaching chemistry concepts to eliminate misconceptions of students by providing an adequate knowledge base and clear understanding of these concepts. There are specific instructional strategies for different concepts that help students change their misconceptions. Teaching methods to overcome misconceptions of acids and bases. We can use different methods to overcome misconceptions in acids and bases. Some of these are use of simple experiments that can be demonstrated or done by the students, use of mental models, actual models, and use of analogical relation between what the students know and the unknown concepts. Acids and bases can be introduced to students by testing different substances for acidity using indicators to show which substances are acid or base, and which are not. When hydrochloric acid HCl is tested with blue litmus, it changes to red, which indicate that it is an acid. Testing sodium hydroxide solution AOAC with phenolphthalein, which is colorless, forms pink solution, which indicates it is a base. Other acids and bases can also be tested in a similar way. Take other substances which contain H and O and test for acidity and basicity. Example: I test pentant CH3 CH2 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 CH3, a liquid hydrocarbon, with blue litmus paper and show that there is no change in the litmus-like acids. I test ethanol CH3 CH2 CH3 with phenolphthalein and show there is no color change. This experiment practically shows that all substances containing H are not acidic, and all substances containing O are not basic. These experiments will make students to understand acids and bases as substances. particle-related Breinstead concept can be introduced by testing electrical conductivity of a solution of acid, base and pure water. Electrical conductivity of acids and bases can be explained by the presence of H+ AC particles and OAC particles respectively as opposite to the non-conductivity of water, which doesn't produce these ions. This can be further explained by the mental model which shows the ions present. pH value can be introduced by measuring the pH of acid solution of different concentration. pH of 0.1 m, 0.01 m and 0.001 m HNO3 solution can be measured, which gives pH of 1, 2, and 3 respectively. It is necessary to show students that concentration of proton and pH are inversely related. When the concentration of H+ increases, pH decreases and vice versa. We can relate this with the analogy of a seesaw, pH versus H+. The category of acids and bases as strong and weak can be shown by measuring the pH of the same concentration of strong acid or base and weak acid or base, and relate it to the amount of H+, particularly in the solution. Measuring pH of 0.5 mHCl gives pH equals 100% dissociated, strong acid. The concentration of H+ will be 10-1 m. In the same way, measuring pH of 0.1 mCH3 gives pH equals 31% dissociated, weak acid. The concentration of H+ will be 10-3 m. This shows that 1 mHCl solution gives 10-1 mH+, while 1 mCH3 gives 10-3 mH+. This confirms that, because it produces more H+ ion, HCl is stronger acid than CH3. The way we measure the strength of the bulbs that we use at our homes, as if a bulb gives a lot of light, it is strong bulb analogous to strong acid, and if a bulb gives a little light, it is a weak bulb analogous to weak acid. In a neutralization reaction, different reactions of acids and bases can be used to show different aspects of neutralization reactions. By adding 10 ml of 1 mHCl to 10 ml of 1 NO in the presence of phenolphthalein, pink solution forms colorless solution, which shows the reaction of equal amounts of acid and base forming neutral solution. Adding 1 m solution of CH3 to 10 ml of 1 m solution of NO in the presence of phenolphthalein, pink solution, the color of the indicator doesn't change, which shows the resulting solution is basic, not neutral. It can be shown in the same way. Combination of 10 ml of 1 mHCl solution and 10 ml of 1 MnH4O solution results in the formation of acidic solution, not neutral. These experiments can show students that neutralization reaction doesn't always form neutral solution, but it can form acidic or basic solution. Teaching methods to overcome misconceptions about states of matter. The particle concept of matter presents advantages and also certain difficulties to students. The particle concept of matter can be associated to each pure matter, a special kind of particle, mostly spheres, as models, e.g., one sphere for one water particle, another kind sphere for one sugar particle, the mixture of both kinds of spheres for the dissolution of sugar in water. The particle model of matter can best be explained to students by showing or explaining how iodine dissolves in ethanol to form a brown-colored solution. When an iodine crystal is added to ethanol, which is colorless, a brown-colored solution is obtained due to the spread of iodine particles in ethanol. If one places an iodine crystal in a glass capillarity and dip it in ethanol, a fine stream of the solution will escape from the capillary and will sink down due to its density. After a while, the iodine spread evenly through the entire volume. The particle model of matter can be introduced through the formation of the solution of two substances. A sphere model experiment can be used to show the formation of the solution of iodine in ethanol. Two types of spheres are used for the model experiment, that is, big spheres a model for the iodine particle, and little spheres a model for the ethanol particle. Fill the surface of a large glass bowl up to 3/4 with small spheres models for ethanol particles. Create some space in the middle and place some big spheres arranged in a square shape models for iodine particles in iodine crystal. Carefully shake the glass bowl until all spheres are mixed and have spread over the bowl. All spheres are in constant movement and mix to form a model for the iodine solution. The characteristics of this model are discussed. A big sphere represents an iodine particle, a little sphere is an ethanol particle, the moving spheres showing the moving particles in the solution. The model experiment is represented through model sketching, and results of both experiments are compared. Through such introductions to the particle model, students develop abstract mental model form concrete models. Concrete and mental models for the three states of matter can be developed in the same way using sphere models. The use of diagnostic questions is one way of exploring students' concept of particle nature of matter. Ask your students questions about their understanding of the particle model of matter. Explore students' thinking by giving situations to explain, such as if you pump air into a soft bicycle tire or football, does the mass increase, decrease or stay the same? Students should select the answer they think is correct. Do the actual experiment to demonstrate that mass would increase. Students will usually respond that mass would stay the same, because gases have no mass. They will be surprised to see the mass increase, so be ready to help them adjust their thinking by encouraging the idea that particles have mass. Examples like this can be extended to encourage thinking about particles' movement. Ask again if the mass would increase. This time, there is no change in mass, as no more gas has been added, but the tire/football has become harder, just as before. So why has this change occurred? Questions and answers can be used to lead students to the idea that the pressure inside has increased, and that this is caused by increased particle movement. Different questions can be asked to test for understanding the particle model of matter, such as a crystal of ice is built up by water particles. In the box, draw a model of how water particles are arranged in a crystal of ice. A balloon is attached to a flask that is filled with air. The bottle is heated with a burner. The balloon inflated. Why does the balloon inflate? What is the effect of heating on the particles of air in the bottle? Mark your answer from the following 8. The particles of air are expanding and getting bigger. B. With heat, the number of particles is increasing. C. Distances between the particles increase and the particles are moving faster. D. The particles of air are moving out of the bottle into the balloon to get away from the heat. E. Mark all answers that are correct in your opinion. A. In ice crystals, the water particles are solid, in water they are liquid, and in steam they are gaseous. B. In water, the water particles are blue, in steam they are invisible. C. The water particles have no color at all. D. Water particles are moving. In steam they are moving fast, in water slow, in ice very slow. E. Water particles are moving in steam and in water, but in ice crystals they are not moving. If. Which of the following explains a little crystal? A. The sugar crystal is dissolving more and more, and the sugar is mixing with sugar. B. The sugar crystal is dividing in a countless number of tiny sugar particles. These particles are mixing with water. C. The sugar crystal is built up by countless tiny sugar particles. In water, the sugar crystal is dividing in these particles. Sugar particles and water particles are mixing uniformly. The answer to these questions will show the students' ideas about the particle concept of matter and helps the teacher to know misconceptions of students and teach to bring about conceptual change. It helps students also to know the wrong ideas they have about the particle concept of matter and make them understand particle behaviors in other situations such as changes of states and chemical reactions. Activity 3.7. Unit Summary. Misconception, in the science education context, refers to ideas that students have about natural phenomena that are inconsistent with scientific conceptions and reflect the complex nature and multiple causes of students' erroneous conceptions as viewed by science educators. The term represents any concept that differ the commonly accepted scientific understanding of the term. Misconceptions result from the interaction between learners and environment. Characteristics of misconceptions are personal, incoherent, unstable and are embedded in students' alternative belief system. Generally, the possible sources of students' misconceptions are 1. Prior knowledge of learner. 2. The use of energy-day languages and metaphors which have different meaning from chemistry terminologies. 3. Teachers not properly understanding and teaching concepts. 4. Social environment. And 5. Textbook. In different areas of chemistry, misconceptions of students have been identified, and in literature there are specific documented misconceptions. Acid-base neutralization, chemical bonding, states of matter, combustion, chemical equilibrium, redox reactions, etc. are some concepts for which misconceptions are identified. Misconceptions may be present before teaching of a topic and also found after teaching has taken place. Some of these misconceptions are persistent and are resistant to instruction. The ineffectiveness of didactic teaching, tutoring, or replacing misconceptions is one problem for persistence of misconceptions in students. Meaningful learning occurs when the learners actively construct their own knowledge. By using existing knowledge, make sense of newly gained experiences. The teacher and student must be aware of the learner's current ideas. Teaching is planned that challenges misconceptions and provides students with the opportunities for conceptual restructuring. Teachers can help students eliminate their misconceptions by providing an adequate knowledge base and clear understanding of these concepts. This shows the impact of learners' preconceptions and misconceptions, or the process of developing new knowledge. Unit delivery approaches, methods, strategies, class observation, debate, matching activity, role play, independent work, presentation, group work, reflections, group discussion, problem solving, questioning. Learners' activity: actively participate in presentations and class discussions. Carry out short action research. Prepare different test items and evaluate for misconceptions. Work on activities, homework, individual and group assignments. Evaluate high school chemistry text for possible misconceptions. Prepare reports and discuss in a class. Using different teaching methodology to overcome misconceptions in selected chemistry topics. Instructors' activities: highlight basic principles on how to challenge misconceptions. Help students on how to identify misconceptions. Facilitate during class discussion, assisting learners during their work on assignments, commenting on students' work on identification of misconceptions. Arrange students into group to evaluate textbooks for possible misconceptions. Evaluate students' presentations. Assessment strategies and techniques. Evaluation of papers presented by students. Presentations. Participation in peer group evaluation. Quality of work done in identification of misconception. Evaluation of portfolio.